Hello all, this is Kumar. I work as a 1D system analyst at Aramco. Today I'm going to present my work on tailored air handling system and variable valve strategy recipe for low-NOx gasoline compression ignition concept in a heavy-duty diesel engine. I'd like to acknowledge my co-authors, Yu Zhang from Aramco and John Watson from Borg Warner. This is the presentation outline. I will start with the motivation, lay out the engine setup and methodology, followed by results, conclusions, and then wrap up with the future work. The motivation for this work is driven by greenhouse gas and NOx emissions regulations. The heavy-duty NOx standards are expected to drop 90% by 2027 from the current 2010 levels. Similarly, greenhouse gas rules also mandate 9% reduction by the same time. Reduction of CO2 and NOx standards simultaneously is very challenging, and advanced combustion concepts are imperative to meet those requirements. Gasoline compression ignition (GCI) is one such advanced combustion concept that potentially offers improved efficiency and emissions by promoting PPCI combustion using gasoline's longer ignition delay. Published data shows that gasoline-range fuels show much improved NOx trade-off compared to diesel. Over the US certification cycle, the part load region, where the pressures and temperatures are controlled, GCI benefits are very favorable. However, low NOx requirements demand high boost and EGR, and that demands efficient air handling system. At high load conditions, in addition to low NOx, there is a challenge for PPCI combustion promotion due to elevated pressures and temperatures. Here, technology like variable valve can be used to control those pressures and temperatures and leverage gasoline's ignition delay for PPCI benefit. However, VVA further burdens the air handling system performance. Hence, objectives in this work were threefold. First, evaluate detailed air handling system configurations to deliver the aggressive flow requirements while minimizing gas exchange losses. Then the selected candidates were analyzed for system response time and flow delivery using transient simulations by GT and co-simulation integration. And next, the best air handling system candidate was evaluated for Miller cycle benefit at high load conditions. The engine conditions that were investigated are shown in this figure and highlighted. The overall goal for this work was to recommend the most optimized air system, including turbocharger and EGR, that can meet the requirements for low NOx heavy-duty GCI. Prior to results, let's look at the engine setup and the simulation methodology. This is a modified Cummins i615 heavy-duty engine. For simulation, we are looking at a state-of-the-art engine system analysis. This is a quick snapshot of the experimental validation of the 1D engine model and close coupling of 1D and 3D CFD modeling methodology that helped ensure high fidelity of GCI combustion trends such as charge mixture composition, pressures, temperatures at intake valve closing, as well as in-cylinder pressure traces predictions by the 1D model. Let's start with the objective one, steady state air handling system analysis. Here we used a 1 to 1.5 engine out NOx targets for gasoline range fuel at compression ratio 16.5. For those, the EGR and boost targets were noted very high compared to the stock diesel calibration at 18.9 compression ratio, which maintained NOx levels from 3 to 4 gram NOx. To meet these aggressive flow requirements, we investigated the following boost system candidates: single stage variable geometry turbocharger, single stage wastegated turbocharger, and a two-stage production turbocharger. For each of these turbocharger, we used 3 different EGR configurations. The performance of the single stage wastegated turbocharger, when we integrated with the high pressure EGR system, we found that there was inadequate delta pressure to drive EGR and hence the flow targets could not be matched.